So I'm happy to introduce our second speaker of today, Matteo Casati from University of Kent, who will talk about Poisson and quasi-Poisson structures for non-abelian integrable systems.
Hello, thank you, Anastasia, and thank you to the organizer for inviting me and giving me the opportunity to speak at this workshop, since I'm usually from outside the Poisson community, strictly speaking, since I'm coming from the integrable systems one. And what I'm going to do today is, in fact, trying to tell you what are the results of some research work that I've been doing recently about using ideas from Poisson geometry, or even kind of from the basic of Poisson geometry to describe non-abelian integrable systems. And to do so, I will start with something that everyone knows, which is a kind of a super short introduction on Poisson bracket, because that's the main object I'm interested in, and you'll see why, you'll see how. So, okay, we know the story of Poisson brackets. A couple of Poisson conferences ago, there was an exhibit and a book by Yvette Kochman-Schwarzbach about Poisson contribution, of course, to the field, kind of a seminal contribution. And this is what, on this slide, you can see how the original Poisson brackets were born. There is the formula by Poisson and the Jacobi identity by Jacobi, even if in this form is not really by Jacobi, but is by by a Russian mathematician whose name, unfortunately, I have completely forgotten in this name. It was kind of a student who attended Jacobi lectures and provided the Jacobi identity in a readable form. But I mean, that's what we know, and that's what we are all taught kind of in basic differential geometry or Poisson geometry course. So what is a Poisson bracket? Well, we have a Poisson algebra, which is a triple of an associative algebra and the Lie algebra with the Leibniz property, basically, and that's what we are always told. Kind of a slogan for this is that a Poisson bracket is a Lie bracket, which is also a derivation of an associative algebra. And that's kind of a very basic idea, of course. And for integrable system or for dynamical system in general, what we really are interested about, what we really need for a Poisson bracket is the fact that we have a mechanical or physical or kind of an abstract system, which is a space, or can be called like a phase space normally, or it's a field space if you're thinking about some kind of field theory, P, and we have a way to extract information from the system, which are observables, kind of in the basic settings. There are smooth functions on the phase space, and over these two sets, which are of course related, but they are not the same. We have a Lie algebra for the observables, and an action of the observables on the space by derivation. The first one, of course, is our Poisson bracket. The second one is Hamiltonian vector fields. And of course, the two are not unrelated, and we have the usual, very well-known anti-isomorphism between Poisson brackets and commutator vector fields on space. This is what I would like to stress at the beginning. This is my introduction, because when we move away from classical finite dimensional systems and we go to either infinite dimensional system, like systems of PDEs or system of differential difference equations, or in another way to non-abelian systems, then these two rows for one bracket are kind of get disconnected, and we must find a way to save both of them in the space we are working with. And this is a very, I won't ever have time to discuss all of this, of course. This is, these are three simple kind of examples of how we use Poisson bracket integrable system. I think that to enter in the mindset, the most useful and still standard one is the use of Hamiltonian formalism for PDEs, and that, which is kind of very well known, and since at least in the integrable system community since the late 60s, early 70s. And this is well, we are interested in function of, let's say, two variables, a space x and time parameter, and this equation and this function obey equation of motions of evolutionary time. So there is the partial derivative of a function with respect to time is some expression that depends on the function and on its derivatives. Possibly, I mean, on time itself, but I mean, I'm kind of going to get the easy way around here, and I will forget about explicit dependence on the time. We have a space of fields that we make as a formal counterpart of the space with these functions u of x live. And the space of fields is modeled by differential polynomials or functions. Of course, differential function are the extension of differential polynomials, so I will kind of keep it easy. Namely, we will have these objects which are polynomials in the jet variables, so in variables that count the formal derivatives of u's, and smooth functions in the generator, I mean, in the function u itself. Of course, here we forget that u and the derivatives of u are actual functions themselves, so we just use them, regard them as symbols. And out of these densities of local function, out of this differential function, we construct the space of local functionals. If someone has a background like more analytical, they normally here they start to screech because I'm integrating without giving details about what I mean by integrating. But this is an idea that actually comes back to, I guess, Gelfand and Dickey, for which the formal space of local functional is a quotient space by the densities of local functional modulo the images of total derivatives. The idea here in the background is that if you have functions that vanish the boundary, vanish at infinity on the space, then you can integrate by part without taking into account boundary values. Or if you are working, as many of the early people here, with the periodic function, you don't have boundary terms, and then your integral operation is, I mean, allows you to integrate. I mean, your integration by parts is what characterizes your space of local functionals, and this is the space where you can integrate by parts, basically. The prototypical example of Hamiltonian PDE is KdV, quadratic equation. Of course, this is, as kind of everyone knows, integrable. It is nonlinear equation. There is this nonlinear term, which is kind of a Hopf-Boussinesq term, and a dispersive term, which are derivatives of the function. And this equation is, well, but Hamiltonian, in the sense that you can write the equation of motion, think to it a little bit like your Hamiltonian vector field, as an operator, P1. Well, Hamiltonian means that you can do it in two different ways, of course. An operator applied to the variational derivative of a local function. This is the same, I mean, the same idea that when you do in classical mechanics Hamiltonian vector fields, you applied your Poisson bivector to the gradient of your Hamiltonian functions. And well, this is how it is for KdV. The idea is that, of course, that by Hamiltonian, that's what I wrote before, means that this not only this equation of motion can be written in these two different ways, but the Poisson bracket between these Hamiltonians, according to either or to both of the Poisson bracket defined by the operator, by this kind of formula, are an involution. And this bracket here on the space of local functional, this is something that I like to stress, is a Lie algebra bracket, but cannot be a derivation of the space of local functional, because the space of local functional is not an algebra. There is not a well-defined product on it. And yet defines an action of the local functionals on the space of local densities by derivations, basically defines the equation of motion by the formulae I showed before. And as usual, I mean, that's what kind of tells us that we are working with our usual, in a sense, Poisson bracket story, is that there is still this isomorphism between the Lie algebra of observables and the algebra of vector fields or evolutionary vector fields generated by them. So now this was kind of an introduction, and I apologize with people who know it, which so that was super trivial, and for people who don't, who maybe may think that I've been too quick, because I would like to kind of get to our main main course today, which is nonabelian systems of equation. Okay, these systems is kind of our let's take it as prototypical or example system. This is a system of ODEs for a function u and v, function of time. And this is the system that I'd like to present to you. It's u dot is u square v minus v u square, and v dot equals 0. And the first time I normally show this, someone in the audience raise their hand and say, oh, this system is trivial. Of course, it's 0 and 0. But is in fact not, because now we take u and v to be element of GLN, so matrices. And of course, the product matrix is not commutative. So this system is not trivial. And despite it may look like a weird construction, this is in fact at least a couple of interesting and remarkable applications, because if your U is not in GLN but in SON, and you take V to be diagonal, this is the system that gives you the equation of motion for a rigid body in Manakov language, according to Manakov's construction. Or if you take U and V to be not in GLN, but to be in GLNM, and you pick m-dimensional block on it on these structures, then this system gives you a periodic Volterra chain. Volterra chain is a differential difference system, which kind of is a many species version of the normal Lotka-Volterra predator-prey interaction. Non-abelian in the sense that it is relevant whether the k+1 and the k this could be the number of people of animals in the k+1 population is multiplied on the left and the k-1 on the right. So non-abelian because of course you get this with this product, and Volterra chain because this reproduces the kind of the non-abelian the version there. This system of equation is in fact integrable. The way to see that it is integrable is that it is what in the community we call lax integrability, namely if you construct this object, this operator, but in fact is a multiplication operator with lambda, a formal parameter, then the evolution in time of L is given by this this commutator of matrices reproduces this equation, and by this equation you have that the traces of powers of L are conserved quantities in evolution of the system. I mean, it's the same case as normal lax integrability for ordinary systems of equation, but this is of course is given. I mean, these L and U are now operators whose entries are metrics, so they are not abelian, and what we do, of course, because we like abstraction, is that we forget that originally these U and V were matrices, and we just decide that we are dealing with function U and V on a space where the product is not commutative, and it's still associative but not commutative, and we decide that we don't want to know anything about the commutation rule in the space. So it's not like quantum mechanics. This is in principle more general because we don't ask anything about the product. Of course, that you can do kind of reduction to get back there, but it's kind of outside the scope of my discussion. And as there are system of ODEs in this class, there are cases of PDEs where you have the non-abelian version of KdV equation. The kind of the linear part is of course the same because you cannot really change much on the linear parts, but the nonlinear one gets kind of the democratic split of the position of UX, or in the differential difference cases where you have this non-abelian Volterra. I mean, the one that I wrote before in block, I can write it as a usual, as kind of as a non-linear equation for a function of two variables, and this is how you write it. More details about non-abelian of Volterra in the parallel session where I will discuss non-abelian difference systems in details. So the point is that, I mean, I've claimed that I want to see whether a system of this kind is Hamiltonian. And facing the question, the matter of what means being a Hamiltonian system here has had I would say, kind of in the last maybe 20 or 25 years, a bit of a large story, because historically, I would say that there is kind of operational, but it's just kind of my nickname, way of discussing it, which is followed, for instance, by Orver and Sokolov. You find different papers by theirs on ODEs systems or PDE systems of non-abelian time. And by this it means that they focus on finding properties and characteristics of the operator that defines the equation of motion as a non-abelian Hamiltonian operator, and they are wondering what that means, and they do classification like there. There is, well, more recently, I would say, an algebraic approach, which I think is very fruitful, and I'm sure that David Fernandez later and Maxime Faron probably tomorrow will spend a big deal of talk about this. Is the story of double Poisson algebras, introduced by Van der Berg in 2008, and the version that is kind of tailored for PDEs by the Sole, Katz, and Valeri. This is more recent, it's 2013, and what they called double Poisson vertex algebras. But of course, what we would like to establish, what I'd like to discuss, is kind of a geometric interpretation of what being a Hamiltonian system in this setting means. There are some ideas about it. I would say originally in the Ping Shu's paper from 1993 or 1994, albeit, I mean, is not clear to me as a member of the Integrable System community, as is this all this discussion relates to a question of motion. And more recently, there are a lecture course by Kiselev, who's called it's called the non-abelian geometry of differential equation. This is much more similar in approach, in spirit, to what I'm going to do. But I'd like to present a version of it that I think it's kind of more appealing to people in the Integrable System community, and in a way more transparent on its geometric properties. And the ideas is as follows. First of all, we need, as I kind of briefly mentioned, distinguish between the space where fields or where functions live, which is the space A of densities of local functionals, and the space of observables, so the space of local functionals. And kind of the formal way to see it, of course, according that you're dealing with ODEs, PDEs on differential difference equation, the spaces are different, but are always of the form free algebra, quotiented maybe according to the inverse relation. If you want to keep into your Laurent polynomial, if you want to work with Laurent polynomials, even if you want to keep into account inverses of your functions, of your matrices. And these are kind of the version with just generators of the algebra for these. Here you are counting jet variables, and here you're kind of counting shifted variables for dealing with difference polynomials. But the setting in general and in abstract is the same. You have a kind of the quotient of a free algebra on one side, and then the quotient of that space by two operations now, by the commutator of the product there. Basically, that means that your elements are trace of polynomials of Laurent polynomials in the space A. Or, well, fine, if you're working with differential system or different system, on top of the trace, you have to put some kind of integration of the integration operation. I mean, more details on that to follow. But the idea is that here you have a trace operation, so you have kind of a cyclic commutativity of your products of monomials. Here you don't have anything. You have just free algebra pushed by possibly the inverse relation. And on this space, okay, let me just work on ODEs for simplicity, so I forget about difference for now. On this space, I have multiplication operators, and these operators, of course, must distinguish whether I multiply on the left and on the right, because the product is not commutative. This is kind of my notation: multiplication of the left, multiplication of the right, and commutators and anti-commutators. I have what is called a double derivatives. The formula here is kind of quite nasty looking. This simply means that you enter with your derivation operator inside a monomial, and if you hit the monomial which corresponds to the variable you are taking the derivatives for, you split the monomial into bits, one on the left before that, one on the right after that. If what you have hit is a positive power, if what you have hit is a negative power, you just use the normal kind of rule for deriving the inverse of a function. So when you split, you put the inverse of the variables you are splitting, one on your side, one on the other. This is kind of nasty looking for people who are not used to it, but the important message is that this double derivative is in fact a derivation. So it has kind of the standard Leibniz property, which is what I'm looking for. Then, oh, this is a nasty slide where I have to define a lot of weird operation on A tensor A and triple tensor of A, just to make the notation. That means, of course, on this A tensor A, which is the space where I land when I take derivatives, I have a structure of inner and outer bimodule by the normal product on A here with this ordering, and this other one, which is kind of switches the ordering of your product. The star basically makes you jump, while the normal product keeps you in the same side. And then you have this other operation, which are kind of this product in the A tensor A. And kind of this tau is the switch of factors. And then, of course, you have a map that takes your A tensor A and collapses it into A.
Matteo, 5-minute warning.
Okay, yeah. Sorry, I must run more than I thought. So, okay, I'm not explaining all the operation in the double tree. The idea is that Van der Berg introduced the double bracket in this A tensor A in this tensor A space, which has a lot of weird properties that I don't really have not really time to discuss. It's important that there's still derivation in the second entry, that has kind of a weird version of skew symmetry and the Jacobi identity, which is odd, but tells you that if you take the trace operation of the multiplication map of elements on A, you get a Lie algebra structure on the space of local functional and kind of a sensible notion of a Hamiltonian vector field. So for ODEs, that kind of works nicely. You have that double Poisson algebras define proper in the sense of integrable system people Poisson brackets on the space of local function. We are very happy about it. There is a proof that I don't have time to discuss. But then we hit, well, examples that I don't have time to discuss. But then we hit an obstacle, which is double quasi-Poisson algebras. I'm not going to discuss very much about the definition because I'm sure that David and Maxime will do it much better than me. But the idea is that if your Jacobi identity fails to be satisfied, but it fails to be satisfied in a very peculiar way, these E of S are the compositions of the identity of your algebra A, which kind of means that since I'm a simple person, I take my algebra A like the one before, so my identity is just one. And having a double Poisson algebra, I've basically landed in this weird case. This weird case that kind of puzzled a lot in the world system community means the operators that define double Poisson algebras are not Hamiltonian operators in proper sense. I mean, geometrically, that means that they don't satisfy the Schouten identity Poisson bracket with itself. I mean, Schouten bracket of the Poisson by vector with itself equals 0, but yet they define a Poisson bracket on the space of local functionals. I mean, I'm sure that people in the Poisson geometry, not maybe in the non-commutative case, but in the standard case, are kind of aware of it because there is this Cartan form, which kind of is the failing of satisfying the Jacobi identity. But this is what happens for quasi-Poisson algebras. And what I've tried to do is rephrase these double Poisson algebras and double Poisson quasi-double Poisson algebras in a geometric way. I'm really sorry. I must move most of the discussion to the parallel session, where I'm introducing what we call theta formalism, but it's kind of a differential gradient manifolds formalism to deal with Schouten bracket in kind of an operational and easy way. And on this space, there must be kind of a double Schouten bracket and an actual Schouten bracket as we are used. Once you have done all this kind of preliminary work, the operator that defines the double Poisson algebra is a Poisson by vector in this sense. So this is an identity. On the other hand, on ground of Poisson by vectors, a Poisson bracket is defined by the double Schouten bracket of P with two local functionals. The Jacobi identity is equivalent to this kind of multi-bracket expression, and we know that, I mean, in all the cases, or the standard cases, we have P with P equals 0, then, okay, Jacobi identity holds true. The action of A is always given in terms of the action of the Poisson by vector on the Hamiltonian, so everything is given in terms of the Poisson by vector. This is kind of going the our main character. But as I told you, the problem is that quasi-Poisson doesn't fail to satisfy the Schouten bracket, and yet satisfies, and this I think it's kind of new, satisfies this expression for all local functionals. So quasi-Poisson is equivalent or at least, yeah, it should be equivalent, in fact, to what in some older paper are called kind of pre-Poisson bracket, pre-Poisson bivectors, but I'm not sure it's a standard. It's a standard language, but this is indeed equivalent to this for any f, which means that of course the Jacobi identity must be satisfied then, because the Jacobi identity is always a triple bracket with it. So whichever you put here, you're going to vanish. And the fact that the relation between Poisson brackets and Hamiltonian, a computation of Hamiltonian vector fields, is in fact kind of given by two brackets like that, which means, to make it a slogan and conclude, that our quasi-Poisson structure define what we call Hamiltonian structure in integrable system, which is kind of confusing, and I appreciate that, because normally we have been taught for all our lives that Poisson and Hamiltonian coincide. That's at least what goes on in integrable system courses, but this is not quite true. Poisson is stricter than Hamiltonian. I mean, whenever by Hamiltonian you mean your Poisson bracket with that does what you want it to do. And this is the story for quasi-Poisson. So quasi-Poisson, gives you a Hamiltonian structure on the local functional because of this expression. At least, right? It's written in this sense. Now, it doesn't really matter whether you are working with ODEs, PDEs, differential difference equation, because this is always the kind of expression where you land. On the other hand, I am not aware, and maybe Maxime knows better, of any quasi-Poisson, nonabelian quasi-Poisson structure defined for PDEs, but only in the original differential case. So this is this exists for ODEs, definitely. This, in principle, might exist, but I have no idea how it looks like for PDEs or differential difference equation. But yet, these expressions are kind of safe, fail-safe, and this is what in integral community we should really look for when we want to discuss whether you have a hierarchy of commuting, then functional quantities, etc., etc. The question whether there are more general structures where these are satisfied, but these not, is still completely open. I'm not sure I can answer, but if someone can, I would really appreciate their
Perhaps that can happen in the parallel session.
Yeah, I think that people are going to be all kind of excited, because I say, not coming from Poisson geometry, maybe many of things that I found as discoveries are trivial for you, and I apologize for that. Okay, this is kind of the slogan of what I kind of planning to do in the parallel session and discussion, but that really depends on interest.
Okay, thank you. Thank you very much for this wonderful talk. Let's all give a round of applause to Matteo, both using emojis as well. Emoji applause, very well. Thank you.